Thank you so much, everybody, for coming to my talk. I know that there were a bunch of other very interesting talks in this slot, so thank you so much for choosing me. But yeah, this is Beyond Sequential Consistency. I'm part of the Bloomberg crowd. I work in specifically an organization called Ticker Plant. Obligatory comment about we are hiring. So if you're interested, let me know afterwards. But cool, we can go ahead and get into it. So starting with an overview quickly for this. So like, what is this talk about? The goal behind this talk here is to talk about the different memory ordering models that are available in C++, specifically along with the performance differences of those models. That's what I think is kind of like the specific value out of this talk. There's been a lot of talks over the years that kind of talk about the different memory ordering models, like what they're for, what their guarantees are. But I've never really seen a talk that does very much in terms of kind of like apples to apples comparison of performance differences between them. And I think that's kind of very relevant because as you move into the weaker memory ordering models, like it's more work for maintenance, it's more work for testing, it's just kind of more work to get it correct. And so like we should have an understanding of like what is the actual performance differential that's associated with this if we're going to actually do all of that work. And so that's kind of specifically what this talk tries to do. We talk about performance for a specific data structure and then also compare across a couple different architectures. So before we actually get into like the meat of the talk, I start with a quick introduction defining terms and core concepts. I want the talk to be approachable to somebody who's not really done very much with lock-free programming before. So if you are familiar, the beginning of it will likely be review. Yeah, we go over core concepts before considering implementations and the different memory models. To actually do the benchmarks itself, we consider an elegant lock-free data structure that is extremely favorable for memory optimization, memory ordering optimization. It's a data structure that I spent a bunch of time working with at a previous job, but turns out that it actually optimizes particularly well, which makes it an interesting case example. And yeah, we consider the different relative performance of different memory models for this queue. And we also consider some surprising outcomes where atomics are like not even necessary, which is interesting. But so before we actually get into the main meat of the talk here, starting out with some disclaimers. So I would argue that lock-free programming is technically cool. It's fun to tell people that you do it, but it tends to lead to complex solutions. It's hard to get right, it's hard to maintain, it's hard to test. In my experience, it's often overused. People just assume it's going to be faster and just go and like write a thing before they really benchmark if they actually need it. So yeah, I cannot stress enough, benchmark, benchmark, benchmark. Computers are surprising. You will often find very surprising results even if you are very confident in your outcome, so make sure that you benchmark as you go. Performance is often usage and hardware specific, so again, it comes down to your particular use case. One thing to keep in mind is that lock-free programming is not actually always faster. Like, it very much depends on your use case. For the most part, with lock-free programming, you kind of exchange doing more work on average for lower latency and better progress guarantees. And so it can be much, much faster for certain use cases, but your mileage may vary depending on your usage. And so one other thing is that this talk focuses on the performance of the data structure itself, and it also chooses a data structure that optimizes very well. So, you know, if in your particular use case, you pull something out of a queue and then you immediately go and like wait on a network socket or something like that, probably the optimizations that we're doing here are not going to be terribly relevant for that particular application. So it again depends on what your usage is and what your usage patterns look like, but cool. Another thing that I just want to start with here is that I had GPT kind of make this image here. The idea is that there's kind of an inherent conflict between performance correctness and maintainability for lock-free programming. So again, really consider if you need it, because it's hard to prove correctness with these things. It's hard to maintain over time. You know, you may have subtle bugs in your implementation that only manifest, you know, once in a blue moon, and they're very hard to debug. So again, just make sure that you're reaching for the really sharp knives on the table with this one. So just make sure that you actually really do need it for your use case. But cool. So getting past all of the kind of initial disclaimers, what do we mean by lock-free programming? Probably makes sense to define our terms here before we get started. Well, so colloquially, usually what people mean here is avoiding the usage of mutexes and system calls to synchronize. So specifically avoiding software locks. Like at the end of the day, if you have a multi-threaded program and you need it to do something useful, there is still going to be some kind of synchronization necessary. Like there's going to have to be some guarantee in terms of how your threads cooperate or interact with each other. So there is still synchronization. It's just trying to do it at the minimum granularity possible. And so we depend on hardware intrinsics that guarantee that certain operations are uninterruptible or atomic. And more formally, lock freedom guarantees that for your algorithm, at least one thread always makes progress. And that maybe doesn't sound like such a strong guarantee. And so what do we really mean by that? Like, what does that look like? So this is bad code. Like, hopefully nobody would write this code, but it works to illustrate my point here. So say that we have like a global counter here, in this case, just an integer, and we want to have this increment function, and we want to make sure that our accesses to this counter are like, serialized and guaranteed to be thread safe across the program. So a very lazy solution that one could do here is just slap a lock on the whole thing, and then just, increment your counter based on whatever value is passed in here. This would be a correct if bad solution. Another bad way that you could do this would be instead, so previously up here we have a mutex and we have a global counter. We now just have an atomic integer at global scope here. We initialize it to 0. Our increment function here now actually calls the load function on stood atomic and then attempts to use compare exchange strong. So the way this function works here is you can see it takes 2 arguments. So we first load the current value of the counter. We then pass in what we expect the value of the counter to be and what we'd like to change it to. And if at runtime the value of the counter is still the same, the hardware will perform the atomic exchange to make sure that the incremented value then takes over for the previous value. And this is not an infinite loop. If this fails, this argument is actually taken by L-value reference. So it will actually be updated to the value that was in place if the exchange fails. And so the thing that is kind of crucial to observe here is that if we make it into this branch, like if we fail this CAS, it necessarily means that someone else succeeded. Like the only way that we can make it into the body of this while loop is if another thread came in here while we were working and itself actually did the work. And so if we fail, somebody else succeeded. And so if we look at actually the assembly breakdown of these 2 implementations, so on the right here, we basically just have our lock comp exchange instruction, which is our atomic compare and swap. And on the left, you can see that we have a call to pthread mutex lock and pthread mutex unlock. And then here is the actual add, which is the work that we're actually trying to do at the end of the day. And so on modern systems, the mutex calls are like quite optimized, but in terms of the ways that these functions are actually specified, there's no formal progress guarantees on these things. Like you call pthread mutex lock, in theory, the operating system could immediately put you to sleep and then kind of get back to you and give you exclusive access to this lock at some time that is convenient to it. On modern systems, these are like very well optimized and you're probably not going to call into the operating system, but there's no formal guarantees on this one where, again, on the lock-free side here, if we fail this comp exchange, if we hit this JNE and go back to label 2, it necessarily means that another thread came through here first and itself made progress. So hopefully that kind of demonstrates what I'm trying to get at here in terms of, on the left side, we could have any number of threads pile up for any amount of time in theory. On the right side, we have kind of stronger guarantees in terms of progress. And so just because I was saying that the previous code was bad code, in actual fact, this is more the code that you would write here. Stood atomic, the atomic class template does actually implement operator plus equals. So you can just write that and then you'll just get the lock add that you actually wanted. So this is the code that you would actually write in practice. But hopefully that gives some kind of understanding of kind of the specific point that we're trying to get at here. So now that we know what we're talking about, let's focus in on the C++ memory model specifically. So starting in C++11, we gained a formally defined memory model that includes multiple different memory orderings. So prior to C++11, the standard actually had nothing to say about threading at all. And obviously people had been writing multi-threaded code in C++ for quite some time before that. But previously you were just dependent on you have to look up the semantics of your operating system, your tool chain, your hardware, and hopefully use a library like Boost or something like that that would abstract all of that away from you and then go off of the library guarantees. But formally speaking, there were no guarantees from the standard. It had nothing to say about threading or any kind of memory memory coherency. But starting in C++11, we did actually get this. And so there are multiple different models. We have relaxed, acquire, release, acquire release, which is just a combo of the previous two, and then sequentially consistent. So for those that are, for the pedantic in the room, there is also consume. My understanding is that it never really worked the way it was supposed to. I think it was also added for a single architecture, if I'm not mistaken, something really exotic. In 26, it's formally deprecated and it's equivalent to acquire. But there is also this thing called consume. If you look at the enum, you'll also see that there as well. But so these are the models that we have moving forward. And so, like, why all of these different orderings? What is this for? What are we actually trying to accomplish at the end of the day? It seems like this is a lot of complexity. Well, so on a modern symmetric processing machine, multiprocessing machine, which is to say any computer that you have used in like the last 20 years, all of your cores are simultaneously interacting with memory. You might have multiple cores in a single CPU. You might have multiple CPUs within different sockets in one machine, all of them interacting with memory simultaneously. And each individual core has its own data cache, meaning that like different cores may have independent copies of the same data. If you're working on the same data, you might have 4 cores on one CPU. You know, for an individual location in memory, you might have 4 separate copies of that particular address in the L1 cache. And so if you're operating on shared data and each core has its own copy of that shared data, like it kind of begs the question of who sees what changes when. Like, do different cores even agree on the relative ordering of events? Like if you have 2 different cores that change 2 values that are sitting right next to each other in memory, for the other cores in the system, are there any guarantees about what order they see those happen in? Are they guaranteed to see it in the same order? Like these are kind of interesting questions that come up once you start removing the locks out of your system. You have to start thinking about this stuff. And so the orderings, the different orderings in the C++ memory model exist to give fine-grained control over this, to like basically allow the programmer to state exactly what they want and to put constraints on the implementation, potentially like minimal constraints to actually get what they need out of the program and bring order to chaos. The way that you can think about it is that C++ defines an abstract memory model with several different available orderings that give different guarantees on how different threads and cores will observe events. And then the hardware vendors and library authors go and leverage the platform-specific intrinsics to actually implement and uphold this model. So that's kind of at a high level what these are for and kind of what they do. In terms of the ways that these are actually implemented at the end of the day, so there's this concept of a thing called a memory fence or a memory barrier. What it comes down to, we don't have to think about this very much most of the time as programmers these days, but modern machines and tool chains can reorder the execution of your code at build, link, and runtime depending on how you actually build it. The optimizer may decide to reorder logically independent operations under the as-if rule. Like in general, the optimizer is allowed to do anything as long as your program runs as if it was the program that you wrote. But also at runtime, the CPU pipeline may decide to reorder instructions based on runtime data dependencies. Like at the end of the day, the CPU's main job, or the system at large, the memory subsystem's main job is to try to ensure that the CPU pipeline never stalls. And so it may decide, like, hey, I can run this other stuff in parallel while I'm waiting for this previous load to resolve. And so this stuff can get reordered at runtime as well. And the cache coherency protocol between those different cores may also cause the loads and stores to be observed in different orders by different threads or cores. And so what a single processor sees may attempt to violate common sense causality from the perspective of the program that you originally wrote. And so this can be really challenging to work with. And so we need a way to actually constrain this so that to put limits on what the implementation can and cannot do in terms of reordering. And so memory fences or memory barriers, it's just 2 different terms to mean the same thing, are the lowest order primitive used to constrain these reorderings. There's multiple different types of fences. You can have a compiler fence, which is basically, I think it's like atomic signal fence or something in the standard library is an example of this. Basically, it exists purely for the build toolchain. Like if you put something like that in your program, you're telling the compiler, like, I need you to not reorder instructions across this source line, essentially. Like I need to know that all of the stores that happen above this and all the stores that happen below this do not get reordered. I need to have this as kind of a particular sequence point in my code. There are also runtime fences. CPUs have different opcodes that they actually respect that constrain the CPU pipeline and memory subsystem to ensure that you can enforce ordering at runtime so that like loads and stores can't get reordered across a specific barrier. There's also multiple types of fences within those categories. There's a store fence, which forbids reordering of memory stores across the fence. There's a load fence, which does the same for loads. And then you can have a combined or full fence, which forbids any reordering across the fence. And you can do this either at compile time or runtime. And these are kind of the tools that are used at the lowest level by the implementation. Like inside of Stood Atomic, like you'll have these things. This is how Stood Atomic actually does its business to put limits on what the implementation can do. I didn't say it at the beginning, but if anyone has questions, please ask. But cool. So at this point now, we know what we're talking about in terms of the memory orderings themselves. And so let's talk about them individually. So the first one that we have here is sequential consistency. So we have a very orderly train station. There's a nice platform. Customers are moving in an orderly fashion to get on their trains. Everything is kind of very clean and pristine. And this is sequential consistency. So with the sequential consistent ordering, there exists a total ordering of all sequentially consistent operations throughout your program that all threads agree upon. So this is a global guarantee with this. Transitive visibility of operations is preserved, which is basically to say that like the runtime behavior of your program appears to uphold the expected causal relationships that you declared in your original source program. Like all threads will agree upon the actual runtime ordering of all sequentially consistent operations. And like if A happened, then B happened, then C happened, all threads will agree on that. And if a thread sees that C happened, it can know that A happened before it. So this is the default behavior. There's a saying in C++ that all of our defaults are wrong. I think this is a situation where we actually do have a good default, which is a nice thing to see. But it is also the slowest behavior. And so like there's actually a fairly substantial cost that comes with this. But this is a reasonable default because it means your program does what you thought it would for the most part. And so to take a specific example here, here we have 3 global atomic integers that are just initialized to 0 at the beginning of the program. And inside of our main implementation here, we have this vector of jthread. If people are not familiar with jthread, I think it was added in C++ 20. It's a joinable thread. It's a thread object that in its destructor calls join, essentially. So it guarantees that when this program will actually wait for all 3 of these threads to terminate. We construct our vector, we push in 3 lambdas, which actually fires up 3 background threads. We then hit the destructor for stood vector, which tries to destroy the threads, which then waits for all the threads to exit. And so in each of these threads here, you can see that we're doing just kind of random pre-increments here. In this case here, we're using the pre-increment operator. We're not saying anything about memory ordering, which means that we are implicitly requesting sequential consistency for these operations. So in terms of what will actually happen here, we have no specific guarantees about what the ordering will be at runtime because the operating system could decide to start any of these threads in any order. It could decide to preempt them and temporarily deschedule them. We could have any ordering actually come out of this at runtime. We haven't put any kind of requirements in place in terms of what the runtime ordering will be. But what we do know for sure is that whatever the ordering is, all threads will agree upon whatever that ordering was. Like, if it's increment A, increment B, increment A, increment C, like whatever it is, every thread will agree upon that. And it is not possible that any threads could have kind of like a disagreement about what the actual runtime ordering was. So that's the guarantee that we get out of sequential consistency. There is a pretty high cost for doing this. The next one that we have here is acquire release. And I don't know that GPT really kind of got what I was trying to get it to do here, because I was trying to get it to put multiple hands on that clock to try to show that like people don't necessarily agree about what time it is anymore. But the clock's doing something. I don't know what exactly, but you can see here we still have a platform. Like the trains are still semi-orderly. The people look a little confused. Things are getting a little weird, but like there's still some kind of sensibility to this. So acquire release is a very interesting ordering. Acquire release usage on a specific atomic variable sets up a synchronization point between threads. This is a lot of text, but I think this actually does a really good job of stating what acquire release accomplishes. So if thread A stores into variable X with release ordering, and thread B loads from that variable with acquire ordering, it is guaranteed that B can see all of the transitive stores that were visible to A at the time it made the store into X. And so to restate that, say that thread A is doing a bunch of stuff. It's processing data, it's creating objects, like it's, I don't know, like writing stuff to global memory. And then finally, it decides to store 5 into variable X with release ordering. If another thread comes along and loads from X with acquire ordering and gets the value 5 that was stored by thread A, it can now see everything that was visible from memory from thread A when it stored that value, essentially. So everything that from the perspective of thread A happened before that store is now transitively visible to thread B. And this is an extremely useful guarantee. It is said that thread B synchronizes with thread A in this case. The way that I think about acquire release is that it kind of, sequential consistency is a global guarantee across all threads in your program, whereas acquire release allows you to kind of set up sets of threads that kind of hand off the ability, like this causal relationship between each other. There are no guarantees given for threads that do not synchronize in this way. And so that's the fundamental thing that's difference between sequential consistency and acquire release, is that for threads that do not synchronize, they have no guarantees about what order they see the operations in. They could see arbitrary reorderings. And so to give another concrete example, I don't know why I used universal initialization there, but not for the other one. But anyway, so I have two booleans at global scope here. One of them is an atomic, one of them is a non-atomic, and I have 2 threads. So I have producer thread and consumer thread. And so producer thread stores true into the non-atomic boolean and then stores true into the atomic boolean with release ordering. And you can see down in consumer thread, we load from atomic with acquire ordering and then try to assert that non-atomic is set. And these store, you can see the memory order release and memory order acquire. These statements implicitly set up a memory fence. And so basically, this right here is a store fence. So this store into non-atomic cannot be reordered below this at any point in the toolchain. Same with this load down here with acquire. Like this load for non-atomic cannot be reordered across this load barrier at any level in the toolchain. And so the guarantee that we have here is that if this branch is taken in consumer thread, it is guaranteed that that assertion will pass. So it's not guaranteed that we'll take that branch because the operating system might decide to run consumer thread before producer thread starts, in which case we won't have stored anything into atomic and we won't take this branch. But if we do take that branch, it is guaranteed that the assertion will pass because to get a little bit more formal about it, the fact that there is a store fence here means that there is a happens before relationship that is established between non-atomic and atomic here. And so when we do the release ordering here, like we are publishing everything that happened before that relation, that store essentially. So this is a guaranteed behavior if we make it into the if clause. But cool. And then finally, we have relaxed. Everybody knew this was coming. It's total chaos. The people are now on the tracks. There's no platform at all. The clock has exploded. It looks like this train is actually literally running off the tracks. I don't know what's happening in this picture, but it's all chaos. And so that pretty well represents the model itself. So the only guarantees if you're using the relaxed model are atomicity, which is to say that like no thread can see a partial write. It's guaranteed to either happen entirely or not at all. And this thing called modification order. So I had never heard of modification order before I started researching for this talk. But basically, modification order means that even though there are no guarantees at all about the visibility of like kind of stores with regard to different stores to different memory locations with regard to each other, there is still a total ordering of writes to that one variable. So you have no ability to reason whatsoever in terms of writes to different memory locations. They can get reordered arbitrarily, but you do still have a total ordering of writes to an individual memory address, if that makes sense. And yeah, it establishes neither a runtime fence nor a compiler barrier, and so can therefore get arbitrarily reordered at either compile or runtime. So yes. So basically what does it mean? What does a total ordering of writes to an individual memory location actually mean? My understanding of that case there. So again, you have no ability to reason about the ordering between different, like the visibility between different memory addresses. But you can't, like all of the threads, you can't see logically inconsistent results with regard to a single location in memory. So like if X happens, then Y happens, then Z happens. If a thread sees Z, it can't later see Y, if that makes sense, for an individual memory location. Yeah, yeah. Any other questions about this from anyone? It's a good question. Thank you. Cool. Awesome. All right, so then the example for this one here, this is a little bit more code, but it's still pretty straightforward. So we have two variables at global scope here that are, again, atomic integers. You can see all of our loads and stores here, everything is done with relaxed ordering across the board. And a valid output from this program is that both threads print 42. And like, how could that possibly happen? Because the value 42 doesn't even show up until halfway through the execution of thread B. And it's not guaranteed to print 42, it's just that 42 is a valid output of this program. Well, what might happen, and this is one of the ways that it might happen a multitude of different ways. The compiler might say, well, for my knowledge of this specific architecture, for whatever reason, for my compiler reasons, I would really prefer to do that store into 2 before I do the load from 1. And so we go and reorder those two things. Perfectly valid. It's allowed to do that. And then at actual runtime, when we go and run this program, the operating system might decide for whatever conceivable reason that it prefers to schedule thread B before it schedules thread A. And so in this particular case here, thread B starts up first. We store 42 into 2. The OS then immediately deschedules thread B and decides to run thread A instead. We load 42 from 2. We store it back into 1. And then the OS starts up thread B again. We load 42 out of 1. And congratulations, now both of the threads think the value is 42. And so it kind of gives you an idea of the kind of craziness that you can see out of this. I don't think that it probably would have been obvious to anyone that this program originally could print 42, but that is a valid outcome of this. And it kind of gives you an idea of the lack of an ability to reason about how your program is going to run. So relaxed ordering gives the implementation total freedom to reorder at any or multiple levels. It gives the programmer very little ability to reason about causal relationships, but it is the fastest model that's available. So those are the memory orderings themselves, if anybody has any questions on any of that. Cool. So to get into a practical lock-free data structure where we can actually apply these orderings and see what the differences are. So I'm going to talk about what I kind of consider to be the prototypical example of a lock-free data structure that is extraordinarily useful, elegant, and fast. It's, of course, a lock-free ring buffer. It uses a circular buffer of memory along with atomic counters to move data between threads. The basic use case is a single producer, single consumer queue, but it can be trivially extended to a single producer, multiple consumer. If anybody was at the talk earlier today on like inter-process synchronization via queues, I actually ended up talking about at the time, I think the term that was used for them was MCAST queues. I end up calling it a broadcast queue, but I end up talking about the same kind of data structure. But yeah, it can be trivially extended to multiple consumers. And to give kind of a high level idea here, this is kind of what we're looking at here. So we have this concept of the infinite array. You can imagine that if the easiest way to implement an inter-thread queue, if you had infinite memory, is to just have 2 atomic counters. You have a producer index and a consumer index. The producer index in queue records where the producer is next going to write a record, and the consumer index records where the consumer is next going to read. And so in queues are performed by copying data into the array and then incrementing the producer index, and dequeues are performed by copying data out of the array and then incrementing the consumer index. And so the consumer can know if there's data in the queue by simply comparing against the producer index and seeing if they're equivalent. Yes. So that's a good question. The question was in this infinite array concept, why does the consumer need to be atomic? It doesn't. It's basically just kind of trying to be consistent with the rest of the presentation. For this trivial example, it would not need to be atomic. But a good question. Thank you. And a key point with this data structure is that indexes increase monotonically, which is to say that they can never decrease. This is actually a very nice guarantee that gives us optimization opportunities in the future. So going back to this example previously, you can imagine here, so the producer is about to write into this record here, and the consumer is about to read from this record here, and it just shoots off to the right, essentially. They just go on forever. Obviously, in practice, we don't have access to, we only have access to finite memory. Like, wouldn't it be nice? But the design can be trivially adapted. So our queue still maintains two atomic counters, a producer index and a consumer index. And the counters are still logically indexes into the infinite array, but we use modular arithmetic to map them into a finite buffer. But we still have the guarantees that the indexes only increase because they are logically indexes into the infinite array. And the buffer is used circularly, wrapping back around to the beginning from the end when we fall off the end. And so I don't really like this diagram a whole lot, to be honest, but this hopefully at least gives some idea here. So the producer is currently writing this record, the consumer is currently reading this record, and we spin kind of clockwise around the buffer as we produce and read values, essentially. And so to give probably a better example, we can actually walk through some operations here. So the starting state for our queue here is just the consumer and producer are both at 0. So the consumer knows that there is not data in the queue because its index is equal to the producer index, which means that there's nothing to read. The producer can then go and write values into the queue, and now the consumer knows that it has 3 records to read because the diff between the two is 3. They kind of continue to move off to the right, the consumer kind of trailing the producer and reading records as it goes. And then we get to the wraparound case where basically, in this case here, there are 10 records in the queue. It probably would actually be a power of 2. It's not a great example, but at the same time, in this case here, we have the queue is of size 10. So even though the producer is at index 12, it's actually going to be writing logical index 12. It's actually going to be writing into index 2. And so the producer in this arrangement has to consult the consumer. Like, the consumer checks against the producer to make sure that they're not equivalent, because if they are, there's no data. And the producer checks against the consumer to make sure that the diff is not equal to the size of the queue, because if it is, then there's no more space to write records. So in terms of an actual program to kind of drive this, so for the initial example here, we're just going to be moving integers. This code actually works very well to test that our queue actually works properly in terms of being a FIFO data structure. So our producer thread here just like spins over all the integers up to 10 billion and just pushes them into the queue one after another. And the consumer pops them back out here and asserts on every one of them to ensure they come out in the proper order. So like, it's actually a pretty strong test in terms of making sure that we have the FIFO behavior that we expect. In terms of the implementation of the data structure itself, so in real code, this would be a class template on like type T. For this case here, this talk is not about templates, so we're just going to consider to start with the case of an integer. So this capacity here being the 15th power of 2, that's just in my testing, that was kind of experimentally the best size for the queue that I got for performance reasons. But in terms of the rest of it here, so we have this constructor that just initializes our counters to 0. We have our push and pop functions. We have a bunch of kind of implementation helper functions. And then down here, the next producer record, this is our producer index, and next consumer record, this is our consumer index. And then the stood array down here, this is just the actual queue storage itself, essentially. And so this is probably about the simplest possible implementation of a ring buffer you could come up with. In terms of the implementation of these functions here, so the push function is also very simple. So you can see here our main predicate is that like while the size is equal to the capacity, we have to back off essentially. This spin counter is just used to keep track of how many times we've had to back off. But in terms of the production here, so this map index function here, this just mods it by the capacity. Since we have this as a power of 2, the compiler is almost definitely going to implement this as a bit mask. You could do that yourself, but I think it reads more obviously this way. And the size is just the producer record minus the consumer record. So if there is if there's space available in the queue, then we just actually go and store into our data array and then increment our next producer record. And since this is a stood atomic and we are using pre-increment, this is implicitly requesting full sequential consistency. If we look at the pop function, this is essentially exactly the same. like to move back and forth between them, you can see there's really not too many differences. The main difference here is that this one sleeps as long as the size is 0. That means that there's no data in the queue. But then afterwards, we just pull a record out off of our consumer index and then increment the consumer record. And again, this is going to be sequential consistency. I have sleep down here just for completeness sake. This is just kind of a very lazy implementation of this. I actually went through a bunch of different variants of this where I had like a spin lock to start with, and then I tried adding like NOP or pause instructions, and then I had like a thing that tried to yield before starting to sleep. In my experience, this was actually just the simplest and easiest and best performing version of it that I had. So that's how this kind of came out. But so we try to spin at least 16 times before we eventually then start sleeping. But yeah. In terms of the rest of the code here, so this print stats function, this is just how I'm running my benchmark essentially. So every second we load the consumer record and then we just diff it against the previous second to figure out what our queue velocity is essentially. And the main implementation just fires up 3 threads, the producer, consumer, and the stats printer, and then just runs until we produce all our records. And this is pretty much the entirety of the code. There's really not too much else. If you run this, this is essentially what you'll get. So I ran this for 600 seconds or 10 minutes, which was probably overkill, but that's what I did. And this is roughly the curve that we get for the queue velocity for this one. So roughly about 10 million operations per second. This was running on a Xeon, like an Intel Xeon like server class chip. And so depending on who you are, I don't know if 10 million records sounds like a lot, but it's really not. It's actually pretty terrible. This particular chip was running at a frequency of 2.6 gigahertz. So like at that frequency, 10 million records per second means that we're using roughly 260 cycles per record. And like our queue is doing absolutely no work. Like we're dequeuing these things and immediately throwing them away. And it's just moving integers. So like this is atrociously bad. We should be able to go substantially faster. Like, why is this so bad? What gives? And if we actually start looking at the code itself here, this is where Compiler Explorer came up. But if we start looking at the code here, we can actually get a disassembly. And it's really nice because the disassembly is actually super like easy to read in this case here. So up here, we load our 2 indexes for the producer and the consumer. We subtract them to get the queue size. We then compare against the size of our queue. If they're not equal, we jump into the production section. Otherwise, we go into our nanosleep. And for the production section itself, so the way this is written right now, we actually load the producer index a second time because sequential consistency requires that. But we then just bit mask it here to lop off the high bits and mod it into our array. We then actually just store it into the queue with a move instruction. And then we have our lock add, which is our pre-increment on the producer index. And then we just increment for the next record. The consumer is essentially exactly the same. The main difference here is that now instead of subtracting, we just compare these 2 records directly. If they are equivalent, then that means that there's no data in the queue. So if they're not equivalent, we jump to the consumption section, which does the exact same thing. It rereads the consumer index, masks it, moves the stuff out of the queue, and then actually increments the consumer index. And then this comparison is actually our assertion check because all of this stuff gets inlined. And so like if we look at this code here, like it's like add, move, comp, like, jump not equal. Like we have conditional branches, we have move instructions, we have bit masks. There's not anything terribly interesting happening in this code except for that lock add. And so the only potential bottleneck in this code is the lock add instruction. Like that has to be where this is coming from. And so lock add is a read, modify, write instruction and issues a full memory fence. And so what this means here is that when we run that opcode there, this has to load the value from memory, it has to then increment it, and it has to store it back. And all of this has to happen as a single atomic step, essentially. Like it cannot be possible for any other part of the system to read an intermediate value here. So we have to, there's a reason that this is called lock. Like it has to actually lock the cache line that this value exists on to be able to accomplish this. And so like, do we really need this? Is this actually required by our data structure here? Well, so since we're using the default API on Stood Atomic, which is to say we're using pre-increment, we're implicitly requesting full sequential consistency. And yeah, by using the pre-increment operator, we are implicitly requesting this read, modify, write, or fetch add. But the thing is that the producer and the consumer are individually single-threaded. Like they're separate threads. Like the data structure at large has to handle the fact that it has two threads hitting it at the same time. But from the perspective of the producer or the consumer, there is no contention. Like they are individually single-threaded. And so like the only reason that we would need a read, modify, write like that is if somebody else was trying to hit the same index at the same time, and they're not. And so like our access pattern here actually does not require full sequential consistency, and we can actually avoid both. And so if we slightly reorganize this code here, so we've now actually refactored this into an explicit load acquire. We then have this has space function here, which just does a load acquire on the consumer record and then just diffs them to get the actual current size. We store back into the queue. And then the store here is actually an explicit store release that's done here. If we look at consume, it's again almost exactly the same. It's just the opposite. So has data now does a load acquire on the producer record and subtracts the two to find out if they're 0 or not. And again, the actual store into the consumer record here is done with the memory order release. So instead of like, the plus plus is really nice in terms of like pretty code, this doesn't look as nice. But this is a lot more explicit about what we actually need out of the implementation here. And if we look at the generated assembly for this, so the compiler got really aggressive in terms of reordering once I did this. So it's interesting. This code in the actual program comes after this code. It actually reversed the order of it. But we can see that we still have roughly the same thing. So we're loading the producer index, loading the consumer index, subtracting them, doing the comparison. And then down here, this is the interesting bit. So this line right here is incrementing the producer index. We then store it into the queue and just, we're done. Like there's nothing else here. Like you can see there's no lock add in this case here. This is all moves, subs, comps, conditional branches, and stuff like that. And if we do this, this is what we actually suddenly get. And so we've gone from roughly 10 million operations per second up to about 170 million, which is like astounding. You can see it's like super noisy. It's bouncing all over the place. But that's like almost a 17x improvement just by like changing around a couple lines in our program. So like that's pretty awesome. And so the new code has literally 0 atomic instructions or offenses on x86 64, which is very cool. At 2.6 gigahertz, 170 million records per second is roughly 15 cycles per record. That's actually so good that I was a little suspicious to start with, but like I have disassembled this. We're looking at the real disassembly. Like it is definitely doing the thing. And in this case here, the test machine has 32 kilobytes of L1 cache and a megabyte of L2 cache. This queue contains only integers. And so the entire thing fits into L2, and about an eighth of it fits into L1. And we have like an extremely predictable access pattern here. We're just scanning over this array over and over again. And so I think this does actually make sense. This queue is too small to be realistic, but it kind of shows what the hardware is actually capable of. Can we still go faster? That's always kind of a fun question. And so this is another GPT image. The idea here is that, so we got a brother and a sister that are both trying to do their morning routine. The brother's got to do his hair and the sister's got to brush her teeth. They're completely unrelated operations. They have nothing to do with each other. There's no overlap in terms of the resource. There's no overlap in terms of what they actually do, but there's only one bathroom. And so they have to wait on each other. And so the tagline here is separate routines, shared resource, false sharing slows everyone. And so the issue here is the way that we've declared these two records down here. This also came up during the inter-process communication talk earlier this morning. But the issue here is that, so the size of this atomic is 8 bytes. So we just have 16 bytes here, and they're right next to each other in memory. So they're almost definitely going to end up winding up on the same cache line. And so, yeah, the current memory layout packs the producer and consumer index directly next to each other. And the problem here is that different cores are going to end up fighting to modify the same line concurrently. So for most memory subsystems, cache lines are the minimum granularity. And so the problem here is, so for Intel chips at least, there's this thing called the messy cache protocol. It stands for modified, exclusive, shared, invalid. It controls like the state transitions that the individual cache lines go through. And so the problem is that we have the producer running on one thread and the consumer running on a different thread. When the producer increments its index because it falls on the same cache line as the consumer, the producer CPU is going to have to invalidate the cache line that the consumer CPU has. And then right afterwards, the consumer is going to have to do the same thing. And so these things are going to end up bouncing this cache line back and forth, fighting for exclusive access to modify these indexes. There is actually a thing in standard C++ that exists to try to solve this, hardware destructive interference size. And so what we can use here is if we declare at the top here, we can just add a nice little like const expr cache line size here. We can actually go and add an align as specifier on these to guarantee that these indexes fall on separate cache lines. So it's now guaranteed that both of these things have to be aligned to a 64-byte boundary, which is the size of the cache line on this particular CPU. And so they're now implicitly both occupying 64 bytes of memory in memory. And so we now know that they're going to fall on different cache lines. And if we go ahead and actually, just by adding this align as specifier and nothing else, we then get this. So we get about like another 20% performance diff or something like that just by adding the align as specifier. This is now averaging something like 220 million ops per second, which is pretty awesome. So overall here, including the align as specifier, there is a huge difference in this particular case here when using different memory orderings. Like I said before, this queue is too trivial to be realistic currently, but how can we make the benchmark more realistic? How can we find out if this is actually a durable effect that continues to manifest over different orders of magnitude? Well, the first thing that we would probably want to do is see how the performance trends as the data gets larger, because right now we're just moving integers. So like we're not really doing a whole lot of work. Well, so this is, my naming is probably not super great. This big fast queue here, this is the one that is aligned and has the memory ordering optimizations. And then the naive queue here is the one that is just straight sequential consistency. And at 64 means that we're now moving 64-byte records. So at 64 bytes, we are still locked to 10 million for the naive queue. We're at about 70 million, so about 7x improvement. At 128, we're still locked to 10 million for sequential consistency, and we're somewhere around 50 million for the fast one, so about 5x. We then go down to about 2x for 256 bytes. We are still locked to 10 million records for the naive implementation. And if we jump to a full kilobyte, then we finally find that the memory copies become more expensive than the actual synchronization itself. But even in this case, you can't really see it because of the scale of this diagram. But the memory order optimized version is running at about 4 million ops per second, and the sequential consistency is running at about 3 million. So you're still getting like a 30% improvement just off of the memory orderings themselves, even at a full kilobyte. And so even at substantially larger data sizes, the performance diff is durable. You have to go to a full kilobyte before the copy is the dominating factor over the synchronization. And even in this case, we save 25–30%, which is pretty cool. How else can we make this queue more realistic? And this is where we get into the MCAST queue that I was mentioning before. So right now we have a single producer, single consumer queue. It's just passing data between two threads. But how can we make this more realistic? Well, so what I call like a work queue, which I think is what people traditionally think of in terms of a single producer multi-consumer queue, is a queue that divides data between a pool of cooperating threads. So it would be something where like you have a work pool, you have like, I don't know, some nicely embarrassingly parallel algorithm that you need to run. You have a producer that just throws pieces of work into a queue, and then you've got some number of threads that just like, take like one thread you have a division here where each data record goes to a single thread that then goes and operates on it. A broadcast queue, by contrast, all consumer threads receive all data. And so in this case, each consumer maintains its own individual queue index. And this is really useful in workflows like semantic analysis, intrusion detection, classification, situations where many different things need to be done on every single data record. So like the specific example that I was using at a previous job, we were doing semantic analysis. We started with semantic analysis, then we were doing log processing. But situations where we're running, tens or hundreds of different classification pipelines on every single data record that comes in. And so it works very nicely to kind of expand out and broadcast this data to all of those different threads. You can kind of think of it like Kafka, except it's entirely in memory and lock-free. So you have different threads that maintain their own indexes and receive all data across whatever topic you're actually receiving data from. But multiple consumers adds a new problem, which is like, how does the producer know if the queue is full? Because there's now many different indexes that it needs to look at. This morning, the solution was either that the producer doesn't care and just overtakes the consumers, which is one way you can do it. The other suggestion was that there was like a special consumer, and that one's supposed to be the fast consumer, and we only look at that one. The solution that we've taken here, or that I took at the time, was to add a new thread whose job is to identify the slowest consumer. Let's call this new thread the collector. And the idea here is that the collector continuously observes the consumer indexes and tries to find the slowest consumer, or the consumer with the lowest index, which it records as its own index and which becomes the edge of the new circular buffer. So the producer now compares against this collector, and the job of the collector is to constantly find what is the slowest consumer in the queue. So we still have a guarantee. In this particular case here, the producer never overtakes any consumer, so every consumer still receives all data, but it only compares against the collector index. In terms of what this actually looks like here, so this like gold kind of outline here is supposed to be the collector. We have two consumers in this queue right now, and obviously a single producer. And so, again, these things kind of move from left to right. So the collector is looking at C1, looking at C1. C1 now overtakes C2 in the next one, and the collector still, identifies the slowest one. And the producer always checks against where the collector is in the queue. So that's kind of how this data structure ends up working. In terms of extending the code that we had, it's a very straightforward modification. So in this case here, we now have this slowest consumer record, which is our collector index. And we now have an array of consumer contexts here instead of a single one. This consumer context is just a struct that is, again, aligned to the cache line size and just like declares a nice little atomic inside of it that is its individual consumer record. And then we still have our primary data array below. And so this is, and then we also have this collect function here. In terms of the collect function itself, it's very straightforward. We just like start with like numeric limits, max size t, and then we just spin over all the consumers to actually figure out which one is the slowest. We just, whatever is the lowest value that we see, we take that and then we store it back into the collector pointer here, or the collector index, so that the producer knows where it can actually go to. And the thing that's interesting here, you can see that we're issuing a relaxed load on all of these things. This is one of the things that's nice about the fact that we have this guarantee where the indexes can only ever increase, because the collector, like, it doesn't actually matter what order the collector reads these in. It doesn't care at all, because worst case scenario, it is just going to pick an overly conservative estimate. Say that it doesn't receive some update from some consumer, it doesn't really matter because the consumer could only have moved forward. And so it's just going to pick a value that is too conservative. And so it still guarantees that the producer cannot overtake any of the consumers, and it makes this very nice and lightweight. Yes. Yeah. No, it's Matt is very correct. That guarantee helps us here because, again, the assumption here, I said before, these indexes monotonically increase. And the question that was asked is that, it's hard to remember. The question that was asked here is basically that we're calling back to the fact that we're loading this with relaxed ordering and this works comes down to, this is a case where that modification order guarantee is actually useful. The fact that even though, like, in terms of reading all of these consumers together, we have no idea how they relate to each other. It's kind of junk from that perspective, but it's guaranteed that we can never read an older value than we previously saw. And so, that works to our benefit here. But it is nice because otherwise the collector really doesn't have to care about anything. It just spins over the consumers and just looks at all of them. Yes. So the question is, what happens if a consumer gets stuck? What happens if a consumer is not regularly moving forward in the queue? The entire queue blocks. It's so that's one of the things where there's a couple different ways you can try to do this. This particular queue refuses to ever move forward past any consumer. In practice, for a production version of this queue, what we ended up doing at the time essentially is just that we would have a watchdog process that would essentially just observe the queue. If there's ever a consumer that got stuck for more than, I don't know, pick a number out of the air, 50 milliseconds or something like that, just kill it, it's dead. Like it got stuck. But yeah, one thing that does generally come out of this approach of not ever allowing the producer to move beyond any consumer is this convoy effect, where the slowest consumer will actually dominate the overall velocity for the queue. And so this does require that things are kind of relatively equivalent kind of computational complexity to make sure the queue moves nicely together. Other ways that you can do it is as was mentioned before, just allow the producer to overtake the queue of the consumers and have the consumers detect if they've been lapped. But yeah, in actual practice, what we would do is just eject the consumer if we found that something was too expensive. But that's a very good question. Thank you. Yes, and I'm sorry, the question again was basically, could you have the producer do the collection action itself? And you certainly could. You could have the producer run the same logic. You just then have the producer doing things that is not just copying data. But yeah. Any other questions? These are good questions. Yes. Yeah, the question was, have we ever thought about doing anything in a batch? So the idea there being basically you have the producer increment many records at the same time, and you have the
If the batch size is 42, just update the count by 42.
Right. So, I mean, you still have to know the fact that there's many different consumers here. You still have to be aware of what the individual consumer states are.
Each consumer,
Yes.
each consumer looks at the producer.
Mm-hmm. 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 Right. Maybe we should talk more about that offline. I'd be interested to hear the idea. Yeah, because we have had situations where we allow the producer to in-queue a batch of records all at once that get dequeued simultaneously. But even in that case, we still needed the consumer at the time. I'd be interested to talk more after the talk. But cool, awesome. Any other questions from anybody? This is really good. Cool, awesome. And I will fix that. I'd like to find out what happens, but cool. But yeah, so if we do this with multi-consumer queue, this is what we end up getting here. So again, fast queue, relaxed queue, naive queue, my name is suck. But these are with 8 threads each. So let's see here. So this is millions of queue records per second. So this is across all of these threads. So obviously we have 8 threads, and in aggregate, we're doing something like 120 million per second. As we go to 16 threads, this is what we see, 32 threads. Even at 32 threads here, we're going from about 10 million up to over 50 million. So we're still getting like, and again, this is 8 threads on both sides here. So we're still getting about a 5x improvement on this one. And let's see, one thing that's really interesting here. So going from like oh, sorry, actually, I'm looking at the wrong thing. I'm misreading my own numbers. These are the relaxed ones here. So yeah, the naive queue is like sitting down at like, you know, like 2 or 3 million ops per second or something like that. So this first one here is like 50 to 100x. But what's interesting here is that now that we've thrown in a huge pile of threads, this relaxed bit here, you can see the diff between the relaxed to the fast used to be something like 20%. Now in this case here, we're getting 10 million to 50 million. So just the difference in the false sharing itself here has now become a very substantially dominating factor because we've thrown more threads into the pool. And so that starts to show that, like, as you start to add more and more threads, that issue of threads fighting over cache lines really starts to become very substantial. And yeah, the naive queue, it's all of the cases are superimposed over top of each other because they're just all the same thing. But yes. So the question again was, am I using CPU pinning for this benchmark? I was not pinning individual CPUs, but I was ensuring the machine that I was running on had 2 sockets and 2 NUMA nodes. So I was ensuring that everything was pinned to an individual NUMA node to make sure that we weren't getting cross NUMA memory accesses, which would have added a lot of noise to this. But good question. Any other questions from anybody? Yes, about this. The question again was the fact that we're not getting any memory fences or atomic instructions emitted. Does it mean that the stood atomic, like acquire release stuff, is basically just a hint to the compiler? In the case of Intel, essentially, yes. But yes, the question is, yeah, how do I guarantee atomicity? Why am I using a power of 2 here? The reason that I'm locking these queues to a size of power, a size that is a power of 2, is simply to make the mask instruction itself as cheap as I can. So the problem is that I don't know how many slides I would have to go back for this, but Is it worth it? No, it's probably wasn't worth it, but I started doing it. Okay, boy, really a long way. All right, I should not have done this. Okay, yeah. So the issue here is for this map instruction here. By making this a power of 2, I can. This is just this is a bit mask. It's just an AND instruction, which is like the cheapest possible thing a CPU can do. If I was making this an arbitrary number that was not a power of 2, this then turns into a modulus, which is a division. And division is like orders of magnitude more expensive than a bit mask. And so like that's the reason why I'm going with the power 2 specifically, just to make the actual mapping into the queue itself as cheap as physically possible. But cool, good question. Yes, the question is I chose the 15th power of 2 to be the size of my queue. In an actual real world version of this, you would make that like a template parameter and you would have that be configurable. In my testing for this particular benchmark, like on the specific machine that I was running it on and the synthetic load that I was using where I was just throwing stuff in and throwing it out, if I changed it, if I went higher or lower, the performance went down. Like, you know, the larger the queue gets, the worse caching performance you're going to get. And the smaller the queue gets, if the consumer gets descheduled and the producer like runs out of space, it's going to have to stop. And so you're kind of balancing between making sure that the queue is large enough that the threads can be slightly desynchronized with each other without having to stop, while also balancing the fact that the bigger that you make the queue, the more cache pressure there's going to be. But so in my experimental testing for this particular use case, 15th power of 2 is the best number that I found. In an actual real world application where you don't just have threads that are just hotly spinning on the queue over and over and over again, you may want more space just to make sure that you have more buffer. But you got a good question. Thank you. Any other questions from anybody? All right. Sounds good. Awesome. So yeah, interesting thought. And this is getting into what I mentioned before. With the require release optimization, this code now issues 0 runtime memory fences. Like, do we actually need statotomic? Like, what is it doing for us? And what happens if we drop it? And so here we have undefined behavior queue. Do not use this. Yeah, so everybody's favorite thing here, I am now synchronizing via volatile. So everybody loves it. But yeah, so it's otherwise the same. I've just dropped all of the statotomic and I'm now using volatile. I've been asked before, why am I using volatile? The answer is, I don't know. Like it's already UB. I'm just trying to encourage the compiler to not break my code. And in terms of the push implementation, so this is exactly the same. I've also dropped this atomic signal fence here. This is what I was talking about before. This is a compiler barrier. I actually don't even know. Well, if I had marked this whole array volatile, I probably wouldn't even need this because then the compiler can't reorder them. But I have the signal fence there just because it's fancy. And it guarantees that the compiler can't reorder these two things because otherwise right now, since this is not volatile, I think the compiler could decide to reorder it if it wanted to. But yeah, so this issues no runtime instructions. This is purely a compiler fence. And the pop implementation is exactly the same as before. It's just, again, and this actually has to be written this way with like the separate plus equals, because it turns out that plus equals on volatile and plus plus on volatile is deprecated. So I was getting a warning. So it has to be done like this. But yeah, it's the exact same. I've just ripped out all of the atomics. And if you run this thing, you find that you actually get the exact same performance and it does actually work, which is kind of entertaining. And so like it does work and the performance is identical. So like, if we actually compare the assembly, it yields essentially the same code gen. And so have we shown that statotomic is unnecessary? Well, so what happens if we try to run this exact same code, undefined behavior queue, on this laptop that I'm currently presenting from? If we try to do that, we find that it immediately explodes. So it's one thing that is nice is to find out that our assertions do actually work. But yeah, this just immediately asserts and dies if I try to run this on ARM. And so like, yeah, good to know that our assertions work. But like, what went wrong? Why does this work on x86 64, but not on ARM 64 with the exact same code? Well, so it comes down to platform guarantees. So From the Intel x86-64 architecture specification, neither loads nor stores are reordered with like operations. Stores are not reordered with earlier loads. Loads may be reordered with earlier stores to different locations. Stores are transitively visible, and stores are seen in a consistent order by other processors. So it's a whole bunch of text. What it basically means is that Intel x86 just implements acquire release like natively. Like on x86, acquire release semantics are just essentially free because the platform is so coherent by default. This is not true, however, on more weakly ordered platforms like ARM and PowerPC. And so even though all of this stuff is academic and totally a no-op on x86, it is not on ARM. ARM requires explicit load, acquire, and store release opcodes to accomplish the same behavior. And if we actually go and use Compiler Explorer again to get a disassembly out of this, it doesn't really matter too much. I'm not gonna read over all of it. But what you can see here is that when we store the producer index, we have this STLR, store release. And when we actually load the producer index and the consumer index, we have this LDAR, load acquire. And so these opcodes are actually adding implicit runtime memory fences to make this work. And so if we build this on ARM without using stood atomic, these memory fences do not get issued and the code blows up. And so like, yeah, okay, so we have an idea that we are missing fences, but like what actually matters here? Yeah, the fence instructions are missing, but why do they matter? Why do we actually need those fences? Well, so let's think about what actually matters here. Does it matter if the producer reads the consumer's operations out of order? Like, what would that even mean? From the perspective of the producer, the consumer does one thing. Like the consumer's job is that it has to read the data before it increments its pointer. But from the perspective, or its index, but from the perspective of the producer, the consumer does one thing, which is increment its index. So we can't possibly read that out of order. Does it matter if the producer reads the collector's operations out of order? Again, no. Like if it reads the collector's operations out of order, it's just going to take an overly conservative estimate. Like it's just not going to see an increase that it could have seen, and it's going to deduce that the queue is fuller than it actually is. But does it matter if the consumers read the producer's operations out of order? And this does matter. And so specifically, it's this little bit down here. So the problem is that we store into the queue, we store into the data array, and then we increment our pointer, and it has to happen in that order. And so the problem is that if it doesn't happen in this order, we get this weird, bizarre situation where the consumer sees the producer move forward before it sees its queue updates. And so yeah, with the release fence on the producer side and the acquire fence on the consumer side, without that, the consumer can see the producer move forward before its queue updates are visible. The consumer then reads junk from the previous iteration, and stood atomic ensures that we always get the correct behavior on all platforms. And what I was actually seeing, which is especially indicative of what's going wrong here, is that every time this assertion would fail, the expected value would be off by exactly the size of the queue. And it's because it was reading the update from the previous iteration. So you need the fences on ARM to ensure that those two things happen in that specific order. And that's why it needs to be a store release here, and the load acquire on the consumer side is particularly important to make sure that these things are actually observed in the proper order. But cool. So if we do this on this particular laptop, this is not a server grade ARM chip, unfortunately. So we really can't directly compare these two things. I don't know that it would be meaningful to do so, but this is what we see on Mac OS. So with the, let's see here, the sequential consistency version up to the fully aligned version, we still have over a 100% improvement. So it still makes a very substantial difference, even at 64 byte records. And with this one, I just dumped directly to 64 to show that it bears out even at large data sizes. But cool, awesome. So a question, yes. Yes. So the question was, at what level does the reordering happen on ARM? And the answer is that the memory subsystem itself, the processor itself, gives different guarantees. Like one way that you can think about it is that on Intel, you're always paying for acquire release because like the platform just gives that guarantee. You remember that whole big slide with all the like guarantees that you get on x86? ARM just does not guarantee those things. And so like the memory subsystem itself just exposes you to more exotic types of orderings than you would see on x86. And so the specific bit here, it's these opcodes here. So like the compiler is prevented from reordering it, but even in the previous example with the signal fence in place, the compiler still couldn't reorder it, but it's actually the runtime fences that prevent it. Good question. Are there any other questions from anybody? Yes. Oh, that's interesting. So the question was that apparently address sanitizer can't deal with atomic. Sorry, thread sanitizer. Yes, thread sanitizer cannot deal with atomic signal fence. That's. Oh, okay. It can't. So let's see here. So you're not talking about. Where did I have this? Come on. You're not talking about. We'll get there eventually. This thing. You're not talking about this thing. Oh, like that actually issues the that's right. Yeah. So I forget that, I guess atomic thread fence is the name of it. There's a version of this that just issues the fence directly without any of the surrounding stood atomic machinery. So unfortunately, the answer on that one is that I've always been using for the purposes of this talk, I was either using stood atomic or not. And with this one, I didn't even try to throw this into thread sanitizer because obviously it was going to blow up. I unfortunately have not encountered that myself, so I don't have an answer for you. But that is really interesting. I had not heard that. Certainly, I would hope that thread sanitizer would support everything in the STL, but that is interesting to hear. Yeah. And the question was, without actually having what do you call it, the fence instructions, what does this look like on the processor level, essentially? But cool. So on x86, it's fairly implicit. So like you still have this guarantee of for a processor to be able to modify a cache line, it needs to have exclusive access to it. So in terms of what that actually looks like, the individual CPUs have these load and store buffers. And so like if a processor wants to modify something that it does not a cache line that it does not currently have in the exclusive state, it has to broadcast, I think it's like I forget what it's called, but it's like a lock for exclusive ownership or something. Read for ownership. There it is. Yeah, exactly. It has to broadcast that out to all of the other cores to say, this is now mine. Now, what's interesting is that goes into the load buffer for the other CPUs. And so like it takes some time for them to be able to see it. And what the fences really control on x86, in my understanding, is the flushing of the load and store buffer so that becomes immediately evident, like as part of the instruction itself. Like if you have like a lock add, that forces, it forces a flush of your store buffers and it forces a flush of all of the other load buffers across the machine so that all the cores see it at the same time. Without having the fence, you don't have that flush. So the other cores will see it eventually, but they have to get to it essentially. But yeah. So the question, if I understood it correctly, is how do we deal with, like, if we want to actually add consumers dynamically and just not have them pinned like I've been doing in this example? So that is actually how the real version of this data structure used to work. The answer is that at the time we had an atomic bitmap. So basically, like, we had a registration process where when a new process would come up, it would actually go through like an allocation process where we had a thread safe bitmap where it would actually basically it would register for a particular consumer context essentially. So it would do an allocation into that bitmap. That would then tell it what index in the actual consumer array is mine. And then that would be the one that it would go and use. But it's a good question. Thank you. Yeah. Any other questions from anybody? Cool. Awesome. So the final optimization, this is one where, to be honest, I originally was thinking like perhaps this was beyond the scope of my talk, but it was just really cool, so I decided to include it anyway. Doesn't have anything to do with memory orderings. Further research encountered a paper that I've linked to here. We'll publish these slides. But basically, this actually suggests further optimizing the cache performance with the introduction of cached indexes for both the producer and consumer. And so this adds an additional cache-aligned index for both the producer and the consumer that hold a previous snapshot of the opposite index. So That probably sounds kind of confusing. We'll get into it. But what's crucial here is that the cache copies are updated only when the producer or consumer would otherwise need to sleep because they have no work. And so this resolves the final remaining cause of cache misses for this simple queue. And so this is what this looks like. So ignore this is a bunch of junk up here. But what's important here is that so we have this next producer record, and then we have the producers. We have the consumer cache for the producer. We also have the next consumer record and the producer cache for the consumer. And so these actually would not even need to be stood atomic. That was actually a screw up in my slides. Yeah. So yeah, the actual version of this that I benchmarked, these were not stood atomic. When I put it on my slides, I screwed that up. That one I know actually I did benchmark properly. But so the interesting thing here is that so like the producer is going to exclusively work on these records as much as it can, and the consumer is going to exclusively work on these indexes as much as it can. And so what's cool about this is that so like you can imagine when the producer first comes up, it finds that there's like, tons and tons of space. And it knows that the consumer is sitting at index 0. But when the producer eventually fills the whole queue and it says, oh, darn, there's no more space, then it goes and reads the consumer index and updates this cache. And the consumer does the same thing with the producer. And so they only hit the other index when they actually need to. And when you think about it, this makes a huge difference because otherwise, even though we've resolved the false sharing issue, because of that modified exclusive shared invalid situation, any time that the producer has to look at the consumer index, it's going to take an L1 cache miss because the consumer will have updated its value. So the producer will look at the consumer index. It will have to load that cache line because it will have an invalid copy. It will have to load it from the other core, work with it, and then it turns around and does some stuff, comes back, and the consumer will have again invalidated its cache line because it's off doing stuff. And so you still have a situation where the cores have to keep fetching, through like the intra-core fabric. Because of the fact that these things keep invalidating each other. And so this is the original version that does not include this optimization. And so you can see we're getting this was actually, in terms of L1 decache misses, this was actually a lot better than I was expecting. But what's interesting here is that we're getting 32% like last level cache misses. So like whenever we whenever we hit the last level cache, like if we miss an L1, the amount of times that we go to actually miss if we hit the last level cache is a third of the time. And that's like super duper expensive. If we take the version of it that adds the individual cache variants, this is what we get. And so you can see that the L1 cache misses did actually go down a little bit. It went down by like 1%, but it's L1, so that's going to make a huge difference. But in terms of last level cache misses, we go from 32% to 0.001%. And you can actually kind of see the difference here just in terms of the total L1 decache loads. We go from about 29 billion up to about 87 billion. And you can see that the two things are running for almost exactly the same amount of time. So we're going a lot faster here. And what we end up seeing, I couldn't even believe this. Like I almost choked on my food when I was benchmarking this because I expected it was going to make a difference, but I did not expect it was going to make almost a 3x difference. And like the numbers that I was getting on this were already so good I could barely even believe it. That this really made me wonder if I had a problem. But I disassembled the thing and it is doing the work. So it really does seem to be just the diff on the cache performance itself. This really seems to remove essentially all sources of cache misses for this synthetic benchmark. You do have to be careful with making too many conclusions about this just because a real world application is not going to have this pristine of a cache ever. It's going to be doing other things. But in terms of this kind of situation where this is also working on integers in this benchmark, in this situation where we're working on very small data, this makes a ludicrous difference in terms of the actual performance. What we can see though, so in this case here, this is working with 64-byte records. So this is the fast queue versus the cached index queue. At 64 bytes, it does still make, 20-30% difference or something like that. But as we start to make the data larger and larger, the effect decays away. It really makes a difference for very small data. A real world use case of this might be something where you're passing pointers through a queue because that's going to be the same size of as a 64-bit int. I think practically speaking, it's still going to be pretty difficult to actually capitalize on this because again, if your program does anything else, probably this caching behavior is going to fall apart, but we have a question. The main thing that I'll say that the observation from Matt is that doing it with the cached indexing here may actually be kind of logically equivalent to the batching that was suggested before, which if definitely means that I should look into that as well. But yeah, I found this to be extremely interesting just because like I never imagined that this was going to be the result that I was going to get. In real world code, like I said, I think it's probably going to be pretty difficult to really take advantage of this level of performance, just because like at 600 million operations per second, it means that we're averaging something like 4 cycles to like move something in this queue, and like at that point you do literally anything, it's going to be the bottleneck. But it is very cool to see. So yeah, I was amazed by this. For small queue sizes specifically, the optimization makes a massive difference. Yeah, our queue is passing integers. A real world use case would be pointers. Decays as data sizes get large. It never seems to perform noticeably worse in my experience. And the interesting thing here, so now this may be because they did the work and discovered that it just doesn't matter for real world applications, but this optimization does not appear to be implemented by either Folly or Boost. So kind of interesting. But cool. So in terms of final caveats and wrapping up, as I said before, this is a data structure that optimizes particularly well. In this particular case here, the performance is massive because the data structure is so naturally well aligned with acquire release semantics. Like in this case here, it was possible to get us down to 0 atomic ops on x86. That is not always possible. Like there are a lot of algorithms where just a compare and swap or a fetch add is just fundamentally necessary and there's no way around it. But in this case, we don't need it. Another thing to be aware of is that on x86, like with x86, it's kind of all or nothing in terms of synchronization. There's not a whole lot of nuance. And so fetch add and compare and swap on x86 always require a full fence regardless of what you ask for. And so that's something that you do have to keep in mind. But benchmark because it definitely always will matter. In terms of other surprising results, so the cache lines on M3 MacBooks are 128 bytes long, which I had not seen before. But the weirdest thing, and I can't explain this, is that the optimum memory alignment in my testing was 64 bytes, and I have no idea why. That doesn't make sense to me. The other thing that I discovered is funny because it was mentioned in the talk earlier today that there is now a version of Apple Clang that does have hardware destructive interference size. It just returns the wrong value. Well, maybe, yeah, exactly, yeah. Yeah, well, because the internet, it was just a Google search that told me that Macs are 128 bytes. Maybe it is 64 because, yeah, my testing was that 64, like 128 was always a pessimization in my testing. But at least on the version of Apple Clang that I have right now, I don't have hardware destructive interference size, so I just had to pin it. But yeah, in terms of conclusions, using the right model for the job can make a massive difference. It depends on your use case. Performance can be hard to reason about. Sometimes it yields surprises. The standard memory models do an excellent job of ensuring that you cannot write better yourself. This talk I originally started working on this talk because I knew that I could get it to work on x86 without stood atomic, but then I discovered I could get just as good with stood atomic, and so there was no reason to do it. Yeah, relaxed atomics can be difficult to reason about, but can be worth it in the right context. And that's everything I got.